Hello everyone, my name is Suresh Kumar. I want to discuss about two-level clipper in the subject called digital electronics. The basics of diode circuits I have already done in some video lectures in the previous classes. If you want to watch those videos, please watch and comment your doubts. Now, for explaining the two-level clipper, I have selected one question like this. In this question, two diodes are there and two reference voltages are there. Additional to that, two resistors are connected in the circuit and some input is given. We have to find the transfer characteristics of this circuit. Here the problem is not only the shape of waveform but also the range of input are not mentioned here. So we have to analyze this circuit. At the same time, the advantage in this circuit is the cut-in voltage not mentioned. Whenever cut-in voltage not mentioned in the circuit, we can assume that cut-in voltage as 0. Why? Because basically the silicon diode cut-in voltage is 0.7 volts, but it is very small compared to the reference voltages, so we can neglect them. So whenever the cut-in voltage not mentioned in the question, we can take it as 0 volts. Now before going into the diode circuit, first of all we have to analyze this resistive network. Why? Because the input voltage Vi not appearing directly to the diodes D1 and D2. By using these two resistors, the input is attenuating at this point. So first of all we have to reduce this resistive network, then we can go for diodes. For that purpose I rearranged the circuit like this. Since these three sections are in parallel, we can interchange as we like. So that's why I replaced the resistor here. Now it is simply a resistive network. This input voltage Vi will be attenuated at this point. I will assume this voltage is Vx. Here we can use potential divider rule. I also explained the potential divider rule in the first lecture. So here the Vx will be product of source voltage and the resistor connected between the required point and the ground, that is Vi into 3R divided by total resistance, that is R plus 3R. So I taken R plus 3R. So if we simplify this, we will get Vx equal to Vi into 3 by 4. So I can rechange this circuit like this. Simply one source Vx and two diodes D1 and D2 and DC voltage is 12 volts and 9 volts. Here positive terminal is connected to D1, so it is plus 12 volts. Here negative terminal is connected to D2, so minus 9 volts is connected to anode of diode D2. So the conditions for forward bias is when anode voltage is greater than compared to cathode voltage, then diode enters into forward bias. Since the cut-in voltage not mentioned here, we can take it as 0. So the condition for diode D1 and D2 is whenever our voltage Vx is greater than or equal to 12 volts, then diode D1 will enter into forward bias and it will conduct. But actually our main theme is we have to compare the input voltage, not Vx voltage. That's why I taken the condition for input voltage. From this we can write Vi equal to 4 into Vx by 3. So this condition can be rewrite for Vi like that. This 12 volt we have to multiply with 4 by 3. So 12 into 4 by 3, 12 will cancel. So for 4 will remain. So Vi becomes greater than or equal to 16 volts. So when Vi is greater than or equal to 16 volts, then diode D1 will enter into forward bias and it acts like a short circuit. Similarly, when Vx is less than or equal to minus 9 volts, diode D2 will enter into forward bias and it acts like a short circuit. Same condition can be right for Vi like this, minus 9 into 4 by 3, so we will get minus 12 volts. So when Vi is less than or equal to minus 12 volts, then diode D2 will enter into forward bias. So as usual in the first case, I taken sine wave as reference input. Since the input waveform not mentioned in the question, I taken sine wave as reference. On the input waveform, I mentioned 16 volts and minus 12 volts, which are reference voltages with respect to input voltage, which we calculated here. 16 volts and minus 12 volts. Vi must be greater than or equal to 16 volts for D1. Vi must be less than or equal to minus 12 volts for D2. So I selected the points at which our input waveform touching the reference voltages like this. For plotting the output waveform, I taken x-axis and y-axis like this. Here there are some cases present in the waveform like this. From this point to this point, our input waveform lying between 16 volts and minus 12 volts. So I consider it as case 1. Next, from this point to this point, our input voltage exceeding both minus 12 volts and 16 volts. I consider this as case 2. Again, from this point to this point, our input waveform lying between the reference voltages 16 and minus 12, similar to case 1. So I consider from this point to this point, this is case 2. Similarly, from this point to this point, case 1. After that, from this point to this point, our input waveform crossing the minus 12 volts, that means its value is less than minus 12 volts. So from this point to this point, it is a special case. I am considering it as 3. Again, from this point to this point, again our input waveform lying between 16 volts and minus 12 volts, that is simply case number 1. So our circuit can be redrawn into 3 different cases: case 1, case 2, case 3. In the case 1, our input waveform lying between 2 reference voltages. So the main circuit can be redrawn like this. Whenever the anode voltage is less than compared to cathode voltage, diode D1 will enter into reverse bias. Similarly, diode D2 also enter into reverse bias. So they will act like open circuit. When there is no connection between these DC voltages and output, these two supplies will not affect this output. So this Vx will directly appear at V0. Similarly, in the case of case 2, our input waveform exceeded the 16 volts, that is related to this 12 volts. So diode D1 will enter into forward bias and acts like a short circuit, and this diode D2 will enter into reverse bias and acts like a open circuit. So this supply voltage 12 volts is directly connected to output, so output becomes 12 volts. Similarly, in the case 3, diode D1 will enter into reverse bias and acts like open circuit, and diode D2 will enter into forward bias and acts like a short circuit. So this minus 9 volts will appear at this output. So if we plot same thing in the graph, we can plot the graph like this. From this point to this point, diode D1 and D2 both will in reverse bias, open circuit, so output will be equal to Vx. So we can plot the graph like this. Whenever touches the point here, the output becomes directly equal to 12 volts. Why? Because diode D1 will be short circuited So 12 volts will appear here from this point to this point. So this voltage is 12 volts. After that, again case 1. In case 1, output is equal to Vx. So we have to plot as it is the structure of input like this. From this point to this point, diode D2 will be short circuited and minus 9 volts will be appears. So minus 9 volts will be appears at this point. After that, again case 1, that means output follows the Vx. So the curve follows like this. Here Vx is not equal to Vi directly but attenuated. So structure is same but values will vary. So this will be the output waveform. From these two waveforms we can plot them transfer characteristics. For plotting the transfer characteristics, we have to consider input waveform on x-axis and output waveform on y-axis. So I also discussed them procedure for plotting transfer characteristics in the lecture 2. So please watch that video. So parallel to x-axis I am plotting another graph which is simply the input waveform, that is sinusoidal waveform like this. This is Vi, this is T. The important values are not the peak values, that is reference voltages 16 volts and minus 12 volts. That's it. We know these two values only. So I will extend the same values to the x-axis of transfer characteristics like this. So on x-axis two values are more important. One is plus 16 volts, another one is minus 12 volts, minus 12 volts at this point. After that, parallel to y-axis we have to plot the output waveform, which I am drawing here like this. I got the waveform like this and its values are here 12 volts and here minus 9 volts. This is output. So I am extending the same values onto the y-axis like this. So this is minus 9 volts, this is 12 volts. So what happened in the output waveform means between the reference values 16 volts and minus 12 volts, when our input waveform is present, the output follows the Vx. So from this point to this point there is a linear relationship between Vx and output. So I am drawing a linear curve like this. After that, whenever our input waveform exceeded the reference voltage 16 volts, output becomes constant and it appears like this 12 volts plus 12 volts. Whenever our input waveform crossed them minus 12 volts, output is fixed and its value is minus 9 volts. So in this manner we can plot the transfer characteristics of given circuit. The basics of all these topics I already explained in the previous lectures. Please watch those videos and comment if you have any doubts. Thank you.